So what about work and energy? So when we were looking at translational motion, we found that the work acting on an object was equal to F delta R cos theta, where theta in this case was the angle between the force and the displacement. Do we have an analogous work for translational motion? Well, if we just take the analogous quantities here, the analogous quantity for force is the torque. Delta R, the displacement, that would be the angular displacement, delta theta, tau delta theta. And then cos theta, this tells us what happens when the force and the displacement are not in the same direction. That's actually a very complicated thing to deal with when the torque acting on an object is not the same as the direction of the angular displacement. So for us, we'll just leave it at that. And actually, that is the rotational form for work, tau delta theta, as long as the torque and the displacement are in the same direction, or opposite to each other. What about kinetic energy? We use the work to determine what the kinetic energy was. The translational form of kinetic energy was 1/2 mv squared. What about rotational kinetic energy? Does something have energy when it's rotating? Well, yeah, it does. It certainly looks like it might have some kind of motional kinetic energy. So what kind of form does an object have when it's rotating? Well, just by using analogous quantities, we might guess that it would be 1/2 v. Well, the analogous quantity to v is omega. And what's the analogous quantity to mass? That would be moment of inertia. And as a matter of fact, that is exactly the form for rotational kinetic energy. So we have a rotational kinetic energy and a translational kinetic energy. So we do. What about potential energy? Well, now that's a little bit different because remember, potential energy just deals with how high something is in the gravitational field. We don't actually have a different rotational kinetic energy. We just have mgh. We'll just leave it at that. So we've got a translational kinetic, rotational kinetic. Let's actually use these in a problem and see how we might take advantage of a conservation of energy that also includes rotational kinetic energy. Okay, here we go. Let's imagine we're going to have a race. And we're going to have a race between a disc and a hoop. And we'll put these up at the top of an incline and we'll put them together and then we'll let them go and we'll let them roll down the incline and we'll see which one gets to the bottom first. Now, let's see if we can analyze this theoretically first and then we'll actually do the race and see what happens. So, we've got them up at the top at first and we'll start them both from rest and we'll let them roll down to the bottom. And what we're going to do is we're going to solve this using conservation of mechanical energy. We're going to assume that there's no work done on these by non-conservative forces. We'll assume that any effects of friction are negligible. So up at the top, initially, we're starting from rest, so we have no initial kinetic energy, but we have potential energy. And we'll assume that both of them are starting from some height h. Then they roll to the bottom. At the bottom, the potential energy is 0. All the energy is kinetic. So we're going to have the initial mechanical equal the final mechanical. In other words, the initial potential, because the initial kinetic is 0, equals the final kinetic, because the final potential is 0. So what do we have? Let's look at each one in turn. We'll start with the disc, and then we'll look at the hoop. Okay, so for the disc, we have the initial potential energy is mgh. We're going to assume that both of them have the same mass and the same radius. And actually, that is true for my disc and hoop here. They have the same mass and the same radius. So, initial potential energy is mgh. That must equal the final kinetic energy. Now, the kinetic energy has a translational part and a rotational part. As the object rolls down, it's going to be translating. The disk is moving translationally, but it's also rotating. So it's going to have some translational kinetic energy and some rotational kinetic energy. So the final kinetic energy will be the final translational kinetic energy plus the final rotational kinetic energy. The final translational will be 1/2 mv squared, where v is the final velocity at the bottom, plus 1/2 I omega squared at the bottom, 1/2 I, now I for the disk is 1/2 mr squared. So there's I, 1/2 mr squared. And now we're going to assume that both the disk and the hoop are rolling without slipping. In other words, we know that omega, the angular velocity, must equal v, the linear velocity, over the radius. Omega equals v over r. So omega squared is v squared over r squared. So this is just the I omega, 1/2 I omega squared term. So multiplying this out, we have that mgh equals 1/2 mv squared. And here we have 1/2 times a half, or 1/4. The r squareds cancel. We have 1/4 mv squared. 1/4 mv squared. So the total final kinetic energy is 1/2 mv squared, the translational part, plus 1/4 mv squared, the rotational part, to give us 3/4 mv squared. Equating that to mgh, dividing both sides by m, multiplying by 4/3, taking the square root, we have v equals the square root of 4/3 gh. And that will be the final velocity of the disk when it reaches the bottom of the incline. Now, what about the hoop? What do we get for that? So here we go. For the hoop, again we have the initial potential equals mgh. We start out with the same potential energy for the hoop. That must equal the final kinetic, which equals the translational kinetic plus the rotational kinetic, still the same. The translational kinetic is 1/2 mv squared, still the same for the disk and the hoop. But now for the rotational kinetic energy for the hoop, we have 1/2 I, but the moment of inertia for the hoop is just mr squared. So 1/2 I omega squared, and again omega will be v over r quantity squared, or v squared over r squared. So what do we get? We get 1/2 mv squared plus, again, the r squareds cancel and we get 1/2 mv squared. So plus 1/2 mv squared. This is interesting. For the hoop, when it rolls down the bottom, half of the kinetic energy is in the translational part and half is in the rotational part. It has equal amounts of energy in its rotational translational motion. So 1/2 mv squared plus 1/2 mv squared is mv squared. We equate that to mgh, divide off the m, take the square root, and we have the final velocity for the hoop is the square root of gh. Now, let's just look at this. Here, for the disk, the final velocity is root 4/3 gh. For the hoop, the final velocity is just root gh. That 4/3 makes this a larger number. So what that means is that we would expect the disk to be moving faster at the bottom than the hoop, which means we would expect the disk to get there first. So if we were to actually do this race, we would expect the disk to reach the bottom of the incline before the hoop. Well, let's try it and see what happens. Okay, here we go. Here's our incline. Here's the hoop. Here's the disk, hoop and disk. I'm going to start these up at the top. I'm going to release these at the same time. Trying to get them to make sure they're going straight down the incline. And let's see which one gets to the bottom first. Here we go. And obviously the disk got there first. Let's try it one more time. There we go. The disk definitely got to the bottom first. So let's take a look at the numbers again. So what's the bottom line? Why is it that the disk got to the bottom before the hoop? Well, the basic idea is right here. The moment of inertia for the disk is 1/2 mr squared. The moment of inertia for the hoop is mr squared. It's easier to rotate the disk than it is the hoop. And I wish that you could actually try this. If you actually hold both of these in your hand and try to rotate them, if you try to rotate the disk, you can do it fairly easily, but if you try to rotate the hoop, it's actually much harder. You can really feel the difference. It's harder to rotate the hoop than it is to rotate the disc. So how does that affect it? Well, as it's rolling down the incline, it's easier for the disc to accelerate down rotationally, so it's easier for it to go down faster, and so it does go down faster, and that's why we end up with the disc getting down there at a faster speed and getting down there first. All right, great. What about anything else? Are there any other analogous quantities that we could look at? Well, sure there are. A very important quantity that we developed from Newton's third law was linear or translational momentum. So we have that the linear translational momentum P was equal to mv. Is there some kind of angular momentum? There absolutely is. Angular momentum we actually write with the letter L. And analogous to the linear momentum, if the linear momentum is mv, what do you think the angular momentum is going to be? Well, just what are the analogous quantities? The analogous quantity to m is I, and the analogous quantity to v is omega. And actually, I'm going to put the direction in this case because this actually is a really important the directions of vectors is always very important, but I really want to emphasize it in this case. This is a very, very important part of the angular momentum that I want us to take a look at. But first, what are the units of angular momentum? They're going to be the units of moment of inertia, kilogram meter squared, times the units of angular velocity, omega, which are radians per second, or I'll just say inverse seconds, dropping the radians, to leave us with kilogram meter squared per second. Now, how can we use this idea of angular momentum? So let's remember tau equals I alpha, and I'm going to put the vectors in there because I want to maintain that vector nature. Alpha, if we look at like an average torque, we know that alpha is delta omega over delta t. So this is I delta omega over delta t. Now let's assume the angular momentum, the moment of inertia. Let's assume the moment of inertia is constant. So I can pull that into this delta here. So I'm going to write this as delta I omega. Now I know that I've just had to make the assumption that I is constant to do that, but the fact of the matter is that this is really the correct form if I is not constant. So if I is not constant, this form is correct, this form is not correct. So we're going to go with this form, and we're going to use this even if I is not constant. But then I omega is the angular momentum, L. So we've got delta L over delta t. So what does that mean? Well, if the net torque is 0, then delta L over delta t is 0, which means what? Delta L, or L, does not change. L is a constant. So if there is no net torque acting on an object, the total angular momentum is constant. It's uniform. This is an amazingly important result. This brings us to the conservation of angular momentum. The principle of conservation of angular momentum states the total angular momentum of a system remains constant, in other words, is conserved, if the net average external torque acting on the system is 0. So as long as there is no external torque, in other words, there could be internal forces creating internal torques, but as long as there is no net external average torque acting on the system, then the total angular momentum remains constant. In other words, it's conserved. This is a very, very important idea. Let's take a look at some physical examples. Okay, so we're going to demonstrate this conservation of angular momentum. My lovely assistant Fred here is going to give me some angular momentum, not too much. And I'm going to stand on this rotating platform to try and minimize the amount of friction that's acting on me. Why? So that we have no external torque. All right, so, and what I'm going to do is he's going to give me some angular momentum while I'm holding these masses away from my axis of rotation. Then what I'm going to do is I'm going to pull the masses in, which has what effect? Well, decreasing r to the masses is going to decrease the moment of inertia. So I'll be decreasing my moment of inertia, and we'll see what kind of an effect that has on my motion if the angular momentum remains constant. All right, so let's see if we can pull this off as well as possible. All right, Fred, thank you. Okay, so what happened? So I'm spinning, I decrease my moment of inertia to maintain my angular momentum. What happens to my angular velocity? The angular velocity has to increase. If I goes down, omega has to go up to maintain a constant angular momentum. Let's try it one more time. Okay, Fred? All right, hopefully you saw my angular velocity increasing before I fell off and added an extra torque, but there we go. Now, let's take a look at one more thing. Now I'm going to add some angular momentum with the angular momentum of the wheel. So I'm going to start this turning. And now I'm going to change the direction of the angular momentum of the wheel. Well, I have to apply a torque on the wheel to change the direction, which then applies a torque on me in the other direction. So, one more. What if I have some angular momentum and allow an external torque to act on it? So what if I have some angular momentum in this wheel, but I allow gravity to act on it and actually apply an external torque? Well, then we should get a change in the angular momentum. Let's see what happens. So the torque from gravity causes the angular momentum to rotate around. But it doesn't fall off my finger. But now there's enough friction that it's tilting down enough that it's actually about to fall off anyways. Okay, there we go. So there is the principle of conservation of angular momentum. I'll see you next time. So Fred, in his infinite wisdom, told me that he uses this yellow stool rather than that rotating platform, and it's a lot easier to do this without falling over and breaking my neck. So we'll try it this way. All right, here we go. Holy cow. So you'll notice when I pull the masses in, I speed up, and when I put them back out, whoo, my goodness, everything's spinning around now. When I push them back out, my angular velocity slows down. So there we go.